So let's look at this problem. Let's say we have, we want to find the area bounded by these curves. Sure, and I don't, so y equals 6 minus x. Y equals the square root of x. Y equals 0. Especially when there's more than two curves, it's usually going to be a good idea to draw the thing. So y equals 6 minus x is just this line. And I think we did one like this last time, but it wasn't exactly the same. So y equals 6 minus x looks like that. It's got intercepts at 0, 6, and at 6, 0. Y equals the square root of x looks like this. And y equal to 0 is this line right there. So if we want to find the area of this region, there's a couple ways to do it. And we'll do it both ways, right? Because a lot of what we're focusing on right now is kind of talking about the different ways you can integrate this. So we can do this using vertical rectangles. Now, if we use vertical rectangles, we have to note that from here to here, the vertical rectangles have square root of x as their upper boundary. From whatever this point is to here, my vertical rectangles have y equals 6 minus x as the upper boundary. So to find the total area, what we're going to have to do is break this up into two intervals. Oops, that's not what I have to do. There we go. So we need to find this point of intersection. You can find it by setting 6 minus x equal to the square root of x. Now, I think I talked a little bit about this last time. A lot of times when people give you problems like this, the numbers are relatively nice. So you could try squaring both sides and solving this. That would be perfectly fine. It would work. If you did that, squaring this, you get 36 minus 12x plus x squared equal to x. Bring the x over, you get x squared minus 13x plus 36 equals 0. Factor, sorry, that's a 36. Factor this as x minus 9 times x minus 4. And you get x equal to 9 or x equal to 4. Well, clearly this point isn't where x equals 9. This is where x equals 4 and y equals 2. If x is 9, it's actually x equals 9 is an extraneous solution. 6 minus 9 is negative 3. Square root of 9 is positive 3. That would be the point that you would get if you extended this down here. Right? These would intersect at 9, whatever. So that's one way to do it, but the easier way to do it is be like, it's probably a number that's easy to take the square root. So if you plug in 0, okay, 6 minus 0 isn't 0. You plug in 1, 6 minus 1 isn't the square root of 1. But if you plug in 4, 6 minus 4 is equal to the square root of 4. So it pays sometimes to check the easy things. So for this first region here, the area of that's going to be the integral from 0 to 4, right? Because we're thinking about how far left and how far right that rectangle can go. And then the height of that rectangle is the top function minus the bottom function, which is the square root of x minus 0. And the width of that rectangle is dx. And then in this region here, so I will mention this region here, you could totally just say, hey, that's a triangle, and I know the area of a triangle. Or you could set it up. That's going to be the integral from 4 to 6. Because again, right, these rectangles can go as far left as 4, as far right as 6. Of the height of that rectangle, which is 6 minus x minus 0. You don't really need the minus zeros, but it is a good idea to think about, oh, you're really doing the top function minus the bottom function when you're finding the height of the rectangle. And then times the width of the rectangle, which is dx. And we could totally calculate that. And I guess we should.
Professor?
Yes.
So how did you get square root of x minus 0 and 6 minus x minus 0? Shouldn't it be like f of b minus f of a, or like top to bottom and then bottom to top?
So, and that's exactly what we have. So if you look at this rectangle, the top of this rectangle is the function the square root of x.
Okay.
The top of this rectangle is the function y equals 0. And then in this region here, the top of this rectangle is the function y equal to 6 minus x. And the bottom of this region, rectangle, is the function y equals 0.
Oh, so like, okay, so the only thing I'm confused on is why don't we like include the square root of x and 6 minus x in the same thing? Is it because of the y equals 0? So we just totally ignore one of them in each integral?
It's not because it's because in this region, right, so in this specific part here, this rectangle has the square root of x as its top.
Yes.
And this region really has kind of nothing to do with the line y equals 6 minus x.
Yeah, it's like irrelevant pretty much for right.
Exactly. On the other hand, in this region here, this region has kind of nothing to do with the square root of x function, right? Its top boundary is 6 minus x. Its bottom boundary is y equals 0.
Ah, okay. Yes, there you go. Yeah, I completely get it now. Thank you so much.
You're welcome. So let's calculate this just because it's good to do. This is x to the 1/2. And the integral of x to the 1/2 is going to be x to the 3/2 divided by 3/2, which is multiplying by 2/3, from 0 to 4, plus the integral of this, which is 6x minus x squared over 2, from 4 to 6. So let's see, plugging in 4, you get 2/3 times 4 to the 3/2 power is 8, because it's the square root of 4, which is 2, and then cube that, and you get 8. You can also do 4 cubed, which is 64, and the square root of 64 is 8. But word to the wise, if you ever have a fractional power, you always want to do the root part first, because it gets smaller, and then the power part next, and it gets bigger. Here, if I plug in, and then if you plug in 0, you get 0. And then, so right, minus 0, okay. Reminds me, I was supposed to. So remember that I was supposed to get a phone call from somebody and they never called me. Frustrating. Oh well. So then if I plug in 6 here, I get 6 times 6 minus 6 squared over 2 minus, if I plug in 4, I get 6 times 4 minus 4 squared over 2. So let's see, 2/3 of 8 is 16/3, plus this is 36 minus 18, so 18 minus 24 minus 16 over 2 is 8. 24 minus 8 is a number. It's 16. So you get 18 minus 16, which is 2. So that's going to be 16/3 plus 2, which is 6/3. So 22/3. And you want to point out, right? So the area of this triangle, which was this part here, was just 2, which is totally correct because the base is 2, the height is also 2, and the area is 1/2 the base times the height. So if you notice that something is a triangle or a rectangle or a circle, you don't actually have to do its integral if you're trying to find the area. You can just be like, hey, I know it's a triangle. I know it's 1/2 base times height. Okay, but here's the thing. This is probably not the way most people would choose to do this problem. Instead of doing it this way, you could do it this other way, where instead of using vertical rectangles, we can use horizontal rectangles. And so in fact, we can draw a whole bunch of them, right? And the idea is that we're just adding up all these rectangles. Again, this is the function y equals 6 minus x. This is the function y equal to the square root of x. This is y equals 0. Okay, so if I want to find the area this time, I'm going to add up the area of all the rectangles. So now my rectangles go as low as y equals 0. and as high as y equals 2. And the area of each rectangle is the length of the rectangle, which is the right function minus the left function. Times the thickness of the rectangle, which is dy. So the right function is y equals 6 minus x, but we have to solve for x. So we get x plus y equals 6. We get x equals 6 minus y. And then the left function, y equals the square root of x, becomes y squared equals x, or x equals y squared. So this would be considered a simpler way of doing it because we're able to write it as one interval. Let's see if it's the same. It should be. So let's see, we're going to get 6y minus y squared over 2 minus y cubed over 3 from 0 to 2. I plug in 2, I get 12 minus 4 over 2 is 2 minus 8 over 3. Minus, if I plug in 0, I get 0 minus 0 minus 0. So don't forget the 0. So 12 minus 2 is 10. 10 is 30 thirds. 30 thirds minus 8 thirds is in fact 22 thirds. So we're good. All right. Let's look at some more area problems. We did those ones last time.
James, I have a question.
Yeah.
So if we were looking at this like horizontally, how come y equals 0 wouldn't like affect, or how come it wouldn't be like the right function? If that makes sense.
I mean, just looking at the picture, right? It's not on the right, right? So what you should really be thinking about when you're thinking about which function minus which function is you should be looking at your rectangle. If I look at just some rectangle in the middle, and let's say I'm looking at specifically, right, that rectangle right there. The right boundary of that rectangle is the function that it touches on the right, which is y equals 6 minus x, or x equals 6 minus x.
Oh, okay, I see.
Left boundary is the function it touches on the left.
Okay, yeah.
I will also point out, in the vertical one, your boundaries are y things, right? It's y as a function of x, right? The top boundary here is what y is equal to. Y is equal to the square root of x. The bottom boundary here is what y is equal to. That's y equal to 0. Same deal over here. The top boundary is y equal to 6 minus x. The bottom boundary is y equal to 0.
Mm-hmm. Okay, yeah, that makes sense.
And here, the right boundary and the left boundary are the things x is equal to. The right boundary is x equal to 6 minus y. The left boundary is x equal to y squared. Okay. Sure. Let's do a few more area between graphs because those ones can be a little bit challenging. And then I think we'll do lots of U-substitution. So let's find the area between, what do we got here? Yeah, sure. I got a few of these. Let's say, so first example, f of x is going to be 3x cubed minus x squared minus 10x. And g of x is going to be negative x squared plus 2x. And I want to find the area between these two things. And what I'll say specifically here is that if you're finding the area between just two functions, you typically do not need to draw a picture. And I mean, we could draw a picture, and maybe I will at the end, but I'm going to do it without drawing a picture to kind of show you how that works. So the first thing we really need to do is figure out where these functions intersect. So we need to set f of x equal to g of x. So let's see, 3x cubed minus x squared minus 10x equals negative x squared plus 2x. Bring everything to the left, I get 3x cubed. The x squareds cancel. Minus 10x minus 2x is minus 12x equal to 0. Factor out of 3x, left with x squared minus 4. factor this as x minus 2 times x plus 2. So our points of intersection are 0, 2, and negative 2. So that means we're going to need two intervals. We're going to need an integral from negative 2 to 0, and then we're also going to need an integral from 0 to 2. Because they might change which one's on top, depending on which interval we're in. So in the interval from negative 2 to 0, which function is bigger, f of x or g of x? Well, I'm going to pick a point, not one of those 2 points, because we know if you plug in 0, f of 0 and g of 0 will be the same, and you won't be able to tell which one's bigger. Similarly, if you plug in negative 2, f of negative 2 and g of negative 2 will be the same. If you pick a point between those two values. So I'm going to pick negative 1. F of negative 1 is, let's see, it's negative 3 minus 1 plus 10, which is going to be 6. And g of negative 1 is negative 1 minus 2, which is negative 3. So from negative 2 to 0, f is the bigger function. So in this region, f is bigger than g, meaning from negative 2 to 0, I need to integrate f minus g. So f being 3x cubed minus x squared minus 10x minus g being negative x squared plus 2x. Okay. It's not a guarantee that they're always going to change which one's on top and which one's on the bottom. So you have to check in the next interval as well. Hey, Daniel, sorry, your internet's cutting out. We're finding the area between these two curves. So we found where these two curves intersected at 0, 2, and negative 2. And then we were checking to see in the interval from negative 2 to 0, which one is larger. We picked the point negative 1, we plugged it in, and we saw that, in fact, f was larger. Now we're going to do the same thing from 0 to 2. For 0 to 2, we're going to plug in x equal to positive 1 and see what we get. So would we be able to do it the triangle way? I'm not sure what you mean by the triangle way. Oh, I see what you're saying. That is what we're doing. I just didn't draw the picture this time. So I'm trying to show how to do this without actually having to draw the rectangles, but we will do that at the end. So from 0 to 2, because we know that in general, when you're integrating something, we're trying to find the area between curves. You're trying to say, okay, I'm integrating the height of my rectangle, which is the top function minus the bottom function, times the width of my rectangle, which is the dx, which is exactly what I have here. In this interval, even though I haven't drawn the picture, this is the top minus the bottom times the width. In this interval, if I pick x equal to 1, f of 1 is going to be 3 minus 1 minus 10, which is, let's see, 2 minus 10 is negative 8. And g of 1 is going to be negative 1 plus 2, which is going to be 1. So in this one, g is larger. So here we're going to do g minus f. It's going to be negative x squared plus 2x minus 3x cubed minus x squared minus 10x. Okay, so here's how this would look graphically. I think I can erase this, right? This is just the word for how I'm fine with it. No, sorry. So graphically, here's what we've got. Sure. So at 0, they're both equal to 0. At 2, they're both equal to 0 as well, because you plug in 2 here, you get negative 4 plus 4, which is 0. And at negative 2, plug in negative 2, you get negative 4 minus 4, so you get like negative 8. So they hit this point, and this point. G of x being the parabola looks like this. F of x being a cubic function, which I'll draw in blue here, is going to hit the same 3 points. We know that in this interval from -2 to 0, f is the bigger function. And in this interval from 0 to 2, g is the bigger function. So it probably does, I don't know, something like this. So that from -2 to 0, we're doing rectangles that look like that, where the height of the rectangle is f minus g. From 0 to 2, we're using rectangles like this, where the height of the rectangle is g minus f.
Oh, James, so pretty much we're just trying to figure out the bigger the y value, that determines pretty much the top and the bottom of the whole thing.
Right.
Oh, for sure. Okay. I get it.
And I will say, in the same sort of vein, if you had to do it horizontally, because your functions were in terms of y instead of in terms of x, then the bigger x value, which would determine which one was the bigger one, which would be not on top, but further to the right.
Yeah, but wouldn't that be rare, pretty much, if we were to have questions like that?
I wouldn't say that's rare. I think that's fairly typical.
Okay.
In fact, my next question has to do with that exactly. So we'll look at that one next.
For sure.
And there definitely was also a homework problem that you guys had to do that was like that, where it was like, which one was it here? For Schulten's class, I think the second to last problem on the homework, where you have to like find the area with two integrals or set it up, and there's like an a, b, b, c, or there's an alpha and a beta, and that's kind of the same thing. So anyway, we'll look at another one for sure. So calculating this is kind of a pain, but there's something you should be aware of. When you do this minus this, well, we already actually did that when we were solving the equation over there, but it looks like the integral from -2 to 0, 3x cubed minus x squared minus x squared cancels out, and minus 10x minus 2x is minus 12x. Now here's the thing. If that's f minus g, then we know for sure that g minus f is the negative of that. So this integral here from 0 to 2, I could do the subtraction. I could be like, well, I know it's the opposite of this. I know it's going to be -3x cubed plus 12x dx. Because I know when I subtract things in the opposite order, they are the negatives of the original thing. We can check, right? I get -x squared minus -x squared, the x squareds cancel. I get 2x minus -10x, that's going to give me a positive 12x. And I get a -3x cubed. Check. So now we integrate. So integrating this, we're going to get 3x to the 4th minus 12x squared over 2, which is 6x squared. 3x to the 4th over 4, sorry. From -2 to 0 plus -3x to the 4th over 4 plus 6x squared from 0 to 2. So calculating that first part, we have to plug in, so be careful, right? For this first one, you have to plug in the 0 first. So you get 0 minus, then you plug in -2, and you get 3 times -2 to the 4th is 16 over 4 minus 6 times -2 squared is 4. Plus, then for this one, you plug in the 2 first, and you get -3 times 2 to the 4th is 16 over 4 plus 6 times 4 minus 0. So these look to be the same. So we should then double it. Let's see what we get. 16 over 4 is 4. So I've got a -3 times 4, which is 12, minus 6 times 4, which is 24. I feel like I'm making a small mistake. No, I'm all right. Just kidding. Plus -12 plus 24. So I end up with -12 plus 12, which is 24. Questions about this? I don't want you to focus too much on, I mean, you definitely need to be able to evaluate these things, but you have to be able to anti-differentiate and plug it in and do the calculations. But the more important part is the ability to set it up correctly and then anti-differentiate. So, and in less words, what I'm trying to say is basically, if you can get to this point here, you've done most of the work. If you were taking a test and were short on time, I would say stop there. Go do the other work, and then if you have time at the end, come back to this and finish it. But getting to this part of the problem shows that you've understood the calculus portion of it, and the rest of it's just putting numbers in for X and calculating things using arithmetic. Which is why a lot of the time on exams, they will give you problems that say set up, but do not evaluate this integral, because they just want you to set it up, but they don't want you to actually have to do all the terrible, heinous work. Not all the time, though. Sometimes they'll definitely make you evaluate things. Okay, let's look at another one. Where'd you go? Let's look at, say, I want to find, sure, the area between these two graphs. Y squared equal to 1 minus x and 2y equal to x plus 2. So it might be kind of unclear at first if we're really thinking of x as a function of y or y as a function of x. To me, kind of the deciding factor here is that we have a y squared, which means I really don't want to solve for y, because if you solve for y, you get y equal to plus or minus the square root of 1 minus x. And that's just not excellent, right? That means we kind of have, it's not really a function, right? It's literally not a function of x, right? Because it fails the vertical line test, which is okay, but it just means it's probably going to be more sensible to solve for x. So x plus y squared equals 1, x equals 1 minus y squared. And here, solving for x, x plus 2y equals 2, x equals 2 minus 2y. And then I can set those equal to each other to find the points of intersection. So 1 minus y squared equals 2 minus 2y. Bring everything to the right. 0 equals y squared minus 2y, and then 2 minus 1 is 1. Uh-oh. This looks worrisome. I feel like this problem might be, now I'm concerned. 2y equals x plus 2. I make a mistake. Did I make it? Let me double check. So I'll tell you why I'm worried. So here's why I'm concerned. These only seem to intersect at one point, right? If you factor this is y minus 1 squared, yeah, and you get y equal to 1. What's going on there? Yeah, that seems problematic. Let me double check one thing real quick. Which problem is that? Let's see. Sorry, that is problem 68. I think I know what the error is, but I just want to double check. Am I just making a dumb error? Sorry, I feel like my brain is not braining correctly. Wow, I did make a mistake. Can anyone find it? It's in the second row. Anybody?
Oh, your signs.
Right. That should be a negative x plus 2y equals 2.
Yeah.
I should have just left the x on that side. So this is good to think about, though, right? If someone's telling you these two things intersect, right? If you're trying to find the area between two curves, it means there should be at least 2 points of intersection, maybe more, right? Like in the previous problem, we had 3 points of intersection, but there has to be at least 2. And since we were only getting 1, we're like, hey, alarm, that's a problem. We probably made an error. So yeah, and I did make an error. So solving this for x, I should get 2y minus 2 equal to x. So I have the wrong signs there. Okay. So this is going to be 1 minus y squared equals 2y minus 2. Much better. Okay. See, it's easy to make little mistakes. We got to be super careful. So then bringing everything to the right, we get 0 equal to y squared plus 2y, and minus 2 minus 1 is minus 3. And that definitely factors as y plus 3 times y minus 1. And then our points of intersection are y equal to negative 3 and y equal to positive 1. And while we can and will graph this, we do not have to. I know that these are going to be my limits of integration. I'm going to integrate from as low as y equals negative 3 to as high as y equals 1. And I want to figure out which of these two functions is the bigger function on that interval. So pick any number between negative 3 and 1. I'm going to pick 0 whenever I can. Since 0 is between these two numbers, that's the choice I want. You can pick negative 1 or negative 2, but 0 is like the easiest thing, so pick 0. So plugging in 0, I get x equal to 1 minus 0. So, right, I guess I could call, if I call this one f of y and this one g of y, f of 0 is 1 and g of 0 is negative 2. So f of y is the bigger function. So that means I'm going to do the bigger function minus the smaller function. That's my f of y, my g of y. Okay. The rest, so we've done the hard part. The rest is not too terrible. I will also point out, so something nice to know. If you've solved this equation, you've already done either f minus g or g minus f. We specifically, right, we had, let's see, g on the right and we subtracted f. So this quantity here, that is g minus f. Since we're doing f minus g, we could just say, well, I know it's the negative of that. So this is going to be the integral from negative 3 to 1 of negative y squared minus 2y plus 3. Or you could work it out, right? I got a negative y squared, I've got a minus 2y, and I've got a 1 minus minus 2, which is a plus 3. I'm just trying to save you some time, right? If you notice these things, you're like, oh yeah, I'm just subtracting in the other order. I've already got that over there. Change it up. So then we get negative y cubed over 3 minus y squared plus 3y from negative 3 to 1. Plug it in, and we get some numbers. Let's see, we get negative 1/3 minus 1 plus 3 minus, and I plug in negative 3. Negative 3 cubed over 3 is going to be negative 27 over 3, which is going to be positive 9, minus positive 9 plus negative 9. It's a lot of 9s. Those cancel each other. So let's see, I've got 3 minus 1 is negative 1/3 plus 2 minus 9. So I should get 11 minus 1/3, which is 33/3 minus 1/3, which is 32/3. If you have set these problems up correctly, you should always get an answer that's positive because you're finding the area between two curves.
James, I have one quick question.
Yes.
So the only thing I'm pretty much not confused on, I get the whole area thing. I think I have it down. But the only thing that, like, I'm confused on is, like, when would you have to, like, you know how we do, like, the integral of something plus the integral of something, like two sets instead of one? Why would we only do one here instead of two?
So to see the answer to that question, let's draw the picture. Okay. So I'm going to erase this because I don't think we really need it. So here's what these graphs look like. If you graph x equal to 1 minus y squared, it looks like a leftward opening parabola. So I'm really just going to plot some points. If y equals 0, then x is going to be 1. If y equals 1 or negative 1, right? If y is 1, x is going to be 0. If y is negative 1, x is also going to be 0. If y is 2, x is going to be negative 3. And if y is negative 2, x is also going to be negative 3. So here's my rightward opening parabola. Sorry, leftward opening parabola. And then 2y equals x plus 2. I didn't, if you solve for x, it's x equals 2y minus 2. So that's a line. I can just find some intercepts. If y equals 0, then x is negative 2. So if y is 0, x is negative 2. And if x is 0, y is going to be 1. Right? So you plug in 0 for x, 2 times 1 minus 2 equals 0. And I feel like this looks a little bit funky. Oh no. Okay. So here's what this looks like. And of course I didn't. So you can see, right, these would intersect over here. Sorry about that. Let me. Anyway, no, I should draw it the right way. So, sorry, I thought I had enough room there. So drawing it a little bit less precisely, it's going to look like this. So here's our region. And the thing about this region versus that first one we did is no matter, so if you do this one horizontally, which is the way we should do it, our right function is always that function, whether I draw a horizontal rectangle there or whether I draw one way down here, right? The right function is always x equal to y squared minus 1. And the left-hand boundary of my rectangle is always the function x equal to 2y minus 2. If you wanted to make this problem harder, you could. And by harder, I mean having to do multiple integrals. You could totally do this vertically. And I guess we might as well look at that for a second just to see. But the idea is that whenever possible, we would always prefer to do one integral versus more than one integral. But if you wanted, you could say, well, I'm going to break this up right here. This is my dividing line. To the left of this line, if I use a vertical rectangle, in fact, let me label these points. So, right, the points of intersection were 0, 1. This point here, y was negative 3, and if y is negative 3, x is going to be 1 minus 9, which is negative 8. Okay, so in this region here, it's kind of a pain in the butt, but for this region, which I'll color in like this, right? The integral for this region would be, well, now my rectangles go left and right instead of up and down, right? So over here, right, when I was using horizontal rectangles, I was doing the right minus the left, and I went from as low as y equals negative 3 to as high as y equals 1. I know I erased it, but definitely have some true. Here, we're going as far left as negative 8, as far right as negative 3. The top function, well, now I have to solve for at y as a function of x. So this was 2y minus 2 equals x. So 2y equals x plus 2, y equals 1/2 x plus 1. So that's my top boundary. Minus the bottom boundary here. So this was y equal to x squared. Sorry, not y equal to x squared. Y squared equals 1 minus x. So this is y equal to plus or minus the square root of 1 minus x. And I should point out this part that is below the x-axis, that is y equal to the negative square root of 1 minus x. This part, that is y equal to the positive square root of 1 minus x. So I hope you guys can all see it's a lot more work to do it this way. Right? We have to think a lot more about what's happening here. So for this one, for this region here, it's 1/2 x plus 1 minus the negative square root of 1 minus x dx. Plus, then we have to do this other dumb region here. So draw a rectangle there. The annoying part about this rectangle is the top function and the bottom function are the same. They're not actually the same because one's the negative, one's the positive. But to find the area of that region, we're going to do the integral from x equals 0 to x equals 1 of the top, square root of 1 minus x, minus the bottom, negative square root of 1 minus x dx. So that's a very long answer to your question. We don't have to do this splitting up thing, because if you do it this way, your ends of your rectangle are always the same. The right end is always this function, the left end is always bounded by that function. Whereas if you do it this way, drawing vertical rectangles, the ends of your rectangles are not always the same, right? From here to here, the ends of it are this function and this function, but from here to here, you no longer have this linear function as your top boundary. You have the parabola as your top boundary.
James, I pretty much understand. So pretty much, you know how we're doing it the horizontal way? It's much better because it's like limiting pretty much the whole graph. If you were to like the x values like limit it, and if you were not to have that, it would infinitely go to whatever, and you can't be doing plus by plus by plus by plus by plus.
Either way is valid and not impossible, but we would prefer to do less intervals. And also the functions are much nicer when you do it the way that kind of makes more sense.
Yeah, of course. Yeah, because you only have to do one integral, and the other one you have to do the two. And yeah.
Now I will warn you, there are some problems where you don't have a choice. Usually, then I feel like they haven't come up as much in 21B as in the 17B classes. But we're not gonna do this one, but I'm just gonna draw a region for you where you might observe that, oh yeah, no matter what you do, you have two intervals. So you can have something that look kind of like this. Let me think for 1 second here. Yeah. You could have something like this parabola, and then also is bounded by like this line and by like this line. So if I was looking at, no, that's still fine. Sorry, it's hard to make up something that sucks. It is possible. I'm just gonna draw something really kind of wacky. Sure, here's some hot trash for you. This region would suck to integrate because whether you use vertical, you've got 3 different top functions. You have to do 3 different integrals, or horizontal. Horizontal would be even worse because this is a breakpoint and that's a breakpoint, and horizontal would be even worse. You'd have 1, 2, 3, 4 different integrals you'd have to do. So basically, when you're trying to figure out which way to do it, you want to see, if I'm drawing horizontal lines, how many different functions am I hitting on the right and left when I go up and down. If I'm drawing vertical lines, how many different functions am I hitting on the top and the bottom. It really depends on what the region looks like. So let's do one more, and then we will move on. Yeah. So, sure. This one is kind of like it. So the area in the first quadrant bounded by y equals x squared, x plus y equals 2, and sure, and y equals 2. And so when you've got more than 2 functions, I do think you want to draw it. Even though y equals 2 is not terrible, it's just a horizontal line. We can draw these things pretty easily. Y equals x squared looks like this. Except, it's the origin like that, right? Okay. And y equals 2, the horizontal line does that. These would intersect at the point 2, 4, and 2, negative 2, positive 4. And then x plus y equals 2 has an x-intercept at 2 and a y-intercept at 2. So that's going to look like this. Okay, and so sometimes it might be good to draw these with different colors. And the problem, I think the problem is a little more specific. It actually says the area in the first quadrant bounded by those 3 functions. So it should be this region right here. And that's the only region in the first quadrant that has y equals 2, x plus y equals 2, and y equal to x squared, whoops, as its boundary. All right, so let me ask all of you. You can type in the chat or you can say words. Is this going to be easier, meaning is it going to require less intervals if we do it using vertical rectangles or horizontal rectangles? Which one's going to be the better way? Vertical, give me a V for vertical, give me an H for horizontal. What's the better way to do this? One more responses. Everybody, there's like at least 10 of you. Thank you, thank you. I see 4, 5, okay. It looks like, so we started with a couple of V's, but now we got a lot of H's. So here's what I want to say. All things being equal, right? Like if it didn't actually matter, I would probably always choose to use vertical rectangles because things are in terms of X. We know how to work with X. It's a little bit more comfortable to work with Y. But in this case, if we use vertical rectangles, we're going to have to do 2 intervals. The reason why is because from left to right, right again, I'm looking at this region here, right here, my vertical rectangle has this function as the bottom. But if I get past this point of intersection right here, then over here, my rectangle has a different bottom function. So, Daniel, I don't know if I agree with what you said at the end though. So I would say vertical. So vertical rectangles means you're doing dx. So vertical rectangle means dx. Means you're integrating with respect to x. Whereas a horizontal rectangle means you're integrating with respect to y. So I would much rather do this one in terms of y, because if I use a horizontal rectangle, the right function is always going to be this function. And the left function is always going to be that function. So I could set this one up using horizontal rectangles and dy. And the interval is going to be, so let's see. I have to find this point of intersection. So again, here's a great time to guess. I've got y equal to x squared, I've got x plus y equals 2. I know this point here is the point 2, 4. I know this point here is the point 0, 2. A good guess might be x equal to 1. And if x is 1, then y is also 1. 1 plus 1 is 2. And if x is 1, y is also 1. Oh, 1, 1 is where they intersect. You could also solve them both for y, right? You could set y equals x squared equal to y equals x, negative x plus 2. And you could solve it that way. And you would get x equal to 1 and x equal to negative, I don't know actually, x squared plus x minus 2, 0, x plus 2, x minus 1. You get x equal to negative 2. So I feel like my, sorry, so that's not too big a deal, but I mislabeled my points. So I need to back up a little bit. I'm annoyed with myself. Sorry, not a huge deal, but it's a big enough deal. This point here is not the point 2, 4. And this is y equals 2, meaning this should be the point where y is 2 and x is the square root of 2. Sorry about that. Similarly, this is not the point negative 2, 4. This is the point negative root 2, 2. This point up here is the point -2, 4, where the graphs would intersect again. Sorry about that. So this point here of intersection is 1, 1. So these horizontal rectangles go as low as 1, as high as 2. The right-hand boundary is y equals x squared. The left-hand boundary is, let's see, it's x plus y equals 2, so it's y equals 2 minus x. Wait, dy? That's a problem. I've made the classic mistake of not changing my functions to be functions of the correct variable, right? So if you're doing a horizontal rectangle, you can't have your functions be functions of x. You have to change them to be functions of y, which is often why we choose to do things in terms of x instead, because often the functions are already written in terms of x, right? Y equals x squared. This one wasn't, but okay. But I would rather do this one in terms of y. So this right-hand boundary, the bigger boundary, y equals x squared. If we solve for x, we get x equal to plus or minus the square root of y. This right side is x equal to the positive square root of y, where x is positive. This left side, where x is negative, is x equal to the negative square root of y. This line, this left boundary, x plus y equals 2. If we solve for x as a function of y, we get x equal to 2 minus y. So the hard way is really a matter of personal preference. I would say it is maybe slightly more challenging to do it this way because you have to write your functions as functions of y, but it is less work overall because we only have to do one integral. If you did it using vertical rectangles, you would have to break it up. This region, you would do the integral from 0 to 1. Sorry, this pen is trash. You do the integral from 0 to 1 of the top minus the bottom, which would be 2 minus the bottom function is y equal to 2 minus x, plus the integral from 1 to the square root of 2. And for this region, you're going as far left as 1, as far right as the square root of 2, of again, the top function minus the bottom function, which is top is 2, bottom is x squared. So part of it is a matter of personal preference. Part of it is a matter of answering the question you're asking. So sometimes people will be kind of sneaky. It'll be like, set up an integral for this area. And although you might be like, oh, I'm doing it either way, you can't, because they said and, meaning a singular integral, which means you have to do it this way. You're not supposed to do it that way. But if they just said, calculate the area bounded by these three curves in the first quadrant, either way would be perfectly fine. Most people would encourage you to do it this way because it's only one integral, but doing it this way is also totally legit. I don't know what to say about not having done any of this in class. That's why it's good to come to code class. You can see it here. I'll do one thing here. Okay, so we can definitely revisit this more in the future, but I think it would be a good idea to kind of shift gears and talk about U-substitution. So let's see, where am I? And I don't recall, remind me please, did we talk about U-substitution at all on Tuesday? We did, okay, great. I don't think we did a whole lot though. So I'll remind you of a few things. When you're doing use, I should say, when you're integrating, when you're anti-differentiating, if you think it might be a U-substitution, your goal is to look for a candidate for U whose derivative is also in the problem, or a constant multiple of its derivative. So for example, if I'm going to do, let's do that, sure. The integral of, say, okay, fine, x to the fifth plus 1 squared x to the 4th. This is a really excellent candidate for u here. U should probably be x to the 5th plus 1. And there are two good reasons for this. Reason one, which I just said, its derivative is also in there, or a multiple. We don't care if you're off by a constant multiple, we can always fix that. So is the derivative of x to the 5th plus 1 in there? Yeah, the derivative of x to the 5th plus 1 is just 5x to the 4th. Do I have a something times x to the 4th? Of course I do. I have an x to the 4th. So that's one reason why, this is really the only reason why this is the good choice for you, is because its derivative is also there. But the way we kind of look for possible candidates for you is we look for things that are stuck inside other functions. And here, this x to the 5th plus 1 is stuck both inside being squared and in the denominator. That's a really good indicator that that's an excellent choice for you. What's that? Oh, sorry. So, the thing here now is we have to change this to being in the variable u instead of the variable x. So one thing I like to do is I'm going to adjust. So I see I have an x to the 4th times dx. I want to make this look like x to the 4th times dx on the right hand side. First and foremost, you're always going to rewrite the derivative here as just du equals your derivative times dx. In fact, a lot of the time we skip this step and go straight to this, that du equals your derivative times dx. But then I have x to the 4th times dx, not 5x to the 4th times dx. So I'm going to divide both sides by 5. We'll say 1/5 du equals x to the 4th dx. Great. Now I can rewrite this integral as, and here's a word of advice, piece of advice. Whenever you're doing a u sub, you always want to make sure you take the things that du is equal to and deal with that part first. So if I'm going to rewrite this integral, I'm going to say, I'm going to ignore that denominator completely for a minute. And just say, I know that x to the 4th times dx, that's 1/5 du. I was going to use blue, oh well. And we usually write our du at the end because that's typical. Okay, now that I've dealt with that, let's deal with the rest. Okay, the rest is I have, well, there's a 1 up there, right? If you factor everything out, this little 1 on top, I have a 1 over u squared. Almost always, we like to factor out any constant multiples. And then, personally, I think it's in our best interest to rewrite 1 over u squared as u to the -2nd. Right? The antiderivative, so I want to point out, because I think a couple people made this mistake on one of the quizzes. The antiderivative of 1 over u squared is not 1 over u cubed over 3. We can't just antidifferentiate that like that. We have to instead say, oh, it's u to the -2nd, and the antiderivative of that is going to be u to the -1st divided by -1. We're not done yet. We started in the language of x, we need to end in the language of x. Or if our function, if our integral is in terms of x, our answer should be in terms of x. So this is going to be negative 1/5 times u, which is x to the 5th plus 1, to the -1 plus c. Or if you prefer, you could write this as -1 over 5 times x to the 5th plus 1. That's right, bringing that down to the bottom. So, darn it, pen on the fingers, never my favorite. Okay, so that's kind of the very basic idea of how these u substitutions work. You're looking for a choice for u whose derivative is always there. So let's look at some other problems.
Excuse me.
Go ahead.
Sorry, I missed when you were talking about how you know which like numbers to use as u to substitute it.
So it's very general. The idea is that we want to make a choice for u so that the derivative of u also is present in our integral. And then the other way I usually look for a choice for u is I look for something that is kind of stuck inside another function, which I know is not very specific, but basically, let me write a couple of examples here. So here are some examples. If I had, say, the integral of e to the x to the fourth times x cubed dx. A great choice for you would be u equal to x to the fourth, because that x to the fourth, well, it's meeting both qualifications. It's stuck inside the exponential function, right? We've got e to the something, and it's also, sorry, one sec. And its derivative is also showing up, right? We've got du equal to 4x cubed dx. So 1/4 u equals x cubed dx. And let me look at one thing here real quick, sorry. Yeah, okay. For the person that asked that question, yes, we'll get back around to that. I promise you, before the end of class, I'll do a problem like the one you asked. But if we also say we had something like, you know, the integral of, let's say we had, so I'm trying to think of like different examples here. But if we had, sure, let's make it easy. X to the 6 times the cube root of x to the 7 plus 1. Well, here, x to the 7 plus 1 is an excellent candidate for you. And I do want to grab the plus 1 as well, because the derivative of x to the 7th is 7x to the 6th. And the derivative of x to the 7 plus 1 is also x to the 7x to the 6th, sorry, 7x to the 6th. And so then 1/7 du would equal x to the 6 dx. Or you could have something like the integral of the natural log of x to the 8th power over x dx. Here, the choice for you would be the natural log of x, because again, it's stuck inside another function. And the derivative here, du is 1 over x dx. And I have a 1 over x times dx. So that's kind of the idea about how we are picking u. Oh, let me give you one more example. Let's say we have the integral of, yeah, let's do that. Let's say we have e to the x times sine of e to the x plus 6. Here, it looks a little tricky, but I notice the e to the x plus 6 is stuck inside the sine function. So that's a good guess for my u. And look, it works out because the derivative of that, well, the derivative of e to the x is e to the x, so my du is e to the x times dx. And look, I exactly have an e to the x times dx. So this is the way I'm picking u. Usually u is stuck inside some function, but I'm more concerned with the derivative of u also being in there.
Okay, thank you.
You're welcome. We should do some of these problems. They're good problems. Let me see here. Sorry. Yeah. So, I mean, they get a little repetitive, but let's go ahead and take a look at like, sure. So, if we actually did this first one here, I would just say, okay, well, my x cubed dx, that's going to be 1/4 times du, and then that's going to be u. So we're going to be integrating e to the u times 1/4 du. And then the integral of e to the u is e to the u. And so we get 1/4 e to the x to the 4th plus c. Let's go ahead and do this x to the 6th time. So here we would let u equal x to the 7th plus 1. Our du is 7x to the 6th times dx. 1/7 du is equal to x to the 6th dx. So my x to the 6th times dx, all that's going to go away and get replaced with 1/7 du. So this here is equal to 1/7 du, and then it's going to be the cube root of u, or u to the 1/3 power. And then we have to do the integral there. So we know a lot of it ends up being using the anti-power rule. You're going to get 1/7 times u to the 1/3 plus 1 is 4/3. Dividing by 4/3 is the same as multiplying by 3/4, plus c. And then 1/7 times 3/4 is 3/28 times u was x to the 7 plus 1 to the 4/3 power plus c. So we have a couple different ones. So let's see here. Where'd you go? What if we had the integral of tangent cubed x times secant squared x dx? This one actually probably technically can be done a number of ways, but there's a better choice. You could let u equal tangent. What's the derivative of tangent?
Secant squared.
I want to have a secant squared, so that's an excellent choice. U is tangent of x, and du is secant squared x dx. So this part here becomes my du, and this part here, well, u is tangent, so tangent cubed is u cubed. So this is the integral of u cubed du, which is u to the 4th over 4 plus c, which is tangent to the 4th x over 4 plus c. I feel like I have one other one I really wanted to do. Sure, let's look at a couple of these. Let's say we have the integral of, sure, let's say we have 3x squared plus 5x plus 1 and 12x plus 10. Sure. Say we have that. So let's see. I'm going to try. So when you have a fraction, the numerator isn't really ever stuck, right? You could totally like pull the numerator out and write it as 12x plus 10 times 1 over 3x squared plus 5x plus 1. But the denominator is something that whatever's in the denominator is kind of stuck there. There's no getting it out of the denominator in a meaningful way. So I'm going to let u equal 3x squared plus 5x plus 1. And I'm going to hope that things work out. Du is 6x plus 5. Do I have a 6x plus 5 times dx? Well, not exactly. But if I factor out a 2 from there, I actually do. I can totally rewrite this as the integral of 2 times 6x plus 5 over 3x squared plus 5x plus 1 dx. Or if you didn't want to do that, you could multiply this by 2 and this by 2 and say that 2 du is equal to 12x plus 10 times dx. Either way, look what I've got. There's my du. So I've got the integral of 2 du over u. I like to factor out the 2. What's the integral of du over u? Well, a lot of people don't like writing it that way. A lot of people prefer we write it as 1 over u times du. It's the same thing. The integral of 1 over u is the natural log of the absolute value of u. So our final answer here is 2 times the natural log of the absolute value of 3x squared plus 5x plus 1 plus c. Okay. So somebody asked I do a question like number 3 in children's homework, which I'm happy to do. It is a little tricky because it's an absolute value, but it's an absolute value and the function inside is non-linear. If it was a linear function inside, you just be like, yeah, I got some triangles. We can find the area of those triangles. But when it's a non-linear function inside, you have to actually kind of work for it. So let me look at the problem here and then I'll make up something a little bit my own flavor here. Let's see here. All right, that's awful. That's really awful. Okay. Yeah, that's a gross looking problem. Okay, then. Also my flyer. Okay, so let's see. I want to find, let's do, sorry, this problem's a little gross. Let's do the integral from -2 to 3, the absolute value of x minus 3x squared, which looks absolutely heinous. Okay, so you don't have to graph it, but I think it's helpful to graph it. So I'm going to graph, let's just graph y equal to x minus 3x squared first. See, it's a downward opening parabola. If I factor out an x, I see that my points of intersection are, or I should say my x-intercepts are x equal to 0 and x equal to what, positive 1/3. So those are my points of intersection. So yeah, here's what the graph would normally look like. I'd hit at 0 and at 1/3 and it would look like this. But the problem is it's an absolute value. So any negative value gets flipped over to being positive. So we actually get, I'm going to draw it again. I'm trying to give myself a little bit more room here. So again, we're hitting at 0 and 1/3, which kind of looks dumb, but whatever. And so it would go like this. But the thing is, it's going to flip the negative parts over. So instead of looking like that, it's actually going to look like that. Instead of looking like this, it's actually going to look like that. Or to draw a less terrible picture. Sorry, my picture is not looking great here. The problem is that these are so close to each other, but I'm just going to make it look a little bit nicer. Basically, you're taking your regular parabola that would look like this. And the negative parts have to flip over. So these are mirror images of each other, and these are mirror images of each other. And it's very sharp and pointy right there. So here is our function. And let's say we're going from -2. Let's be a little less judicious here. Let's say that's -2. There's 0. There's 1/3. There's 3. I know it's not to scale. It's fine. So we need to find those 3 areas, which is going to mean we need 3 integrals. Okay. So this piece of the function right here is y equal to x minus 3x squared. But this piece here, from -2 to 0, it's not y equal to x minus 3x squared. Let me ask you guys, it's a really easy question. What's the absolute value of 5?
5.
Okay, let me ask you a different question. What's the absolute value of -5?
5.
How do you get 5 from -5?
You gotta add a negative sign on the outside.
Right. So here's the thing. If the function originally was negative, the absolute value of that is going to be the negative of your negative function. So right here, the function is actually y equal to -x minus 3x squared. And it's also the same over here. Over here, it's y equal to -x minus 3x squared. Gross. So then here's how we have to find, here's how we're going to find the area of this. We're going to do the integral from -2 to 0 of this function, negative x minus 3x squared, plus, so that's this area in red here. And then let's change up the colors. Running out of colors will be okay. So then this area in black, well, that was still good for a minute anyway, is going to be the integral from 0 to 1/3 of x minus 3x squared. And then lastly, this area in, what have I got? I got blue, sure. Blue maybe. Yeah. That's going to be the integral from 1/3 to 3 of, again, negative x minus 3x squared. Kind of a huge pain in the butt. But that's how you deal with absolute value integrals when you can't just say it's like a triangle. The parts that are getting flipped over from what they would normally be get a negative in front of them. The parts that are just normal without having been flipped over, they just are as is. So the rest of this is just the terrible part where you have to do the antiderivative and plug in your stuff. And yeah, it's awful. I'm not going to do that because I think from this point you can handle it. So for problem 3 in Schulten's homework, the work you're going to have to do is very, very, very similar to this. Yeah. Fun times. Okay. Let's talk about some definite integrals with U-substitution. So definite integrals with U-substitution. Let's see here. Getting all kind of this info here. There was something else I was thinking about. Oh, that okay. Yeah. I'm gonna write a quiz for you guys as well to post up sometime today. We'll get that eventually. Again, don't sweat the quizzes too much, right? Like your actual quiz in your actual 21B class is way more important than the quiz you have to take for this class. But eventually, sometime get around to it, right? After I post it. Let's see, where'd my examples go? Let's look at, sure, you're fine. Let's look at this not too terrible example. Let's find the integral from 0 to 3 of 2x times, what'd you get? X squared plus 1 to the 5th. Could you multiply this out? Yes, you could. Should you multiply it out? No, you shouldn't. So there are 2 valid ways, well, 3 technically, if you multiply it out, but there's a couple ways you could do. Oh, actually, no, yeah. So we're going to do a U-sub here. And in the first method, we're not going to change limits of integration. So we're going to not change our limits of integration. I'm still going to make the same choice for u I'd make either way. My u is going to be x squared plus 1. In fact, I'm going to make this, let's make that 50 instead. Sure, you could technically multiply x squared plus 1 to the 50th, but it'd be a lot harder. X squared plus 1 to the 5th, I could actually multiply if you guys really want me to. I'm not going to. So then my du is going to be 2x dx. And look, we're in good shape. There's my du. So this is going to be the integral of du, and then that's going to be u to the 50th power. Okay. So, I changed it. Yeah, I'm going back for that. We'll do 5. 5 is better because I ignore my answer. Okay. Sorry, I know. Anyway, so here's the thing. My limits of integration are x values, right? This is saying we're going as far left as x equals 0 to as far right as x equals 3 for this function of x. And now I've got a different function of u, and it would not be correct to say that u went from 0 to 3. So one way people would sometimes do this is say, I'm not going to write limits of integration at all. I'm just going to do this. I'm going to anti-differentiate it. I'm going to get u to the 6th over 6. And then I'm going to write that as, I'm going to plug back in what u is equal to, which is x squared plus 1 over, to the 6th over 6 from 0 to 3. Now, personally, I don't love this because it still feels like you're kind of still missing a little something. But if you do this and you plug in 3 for x, you get 3 squared plus 1, which is 10 to the 6 over 6. Minus you plug in 0, you get 1 to the 6 over 6. 10 to the 6 is a million. Minus 1 is 999,999 divided by 6, which would reduce to 222,222 over 3. I don't really care, but fine, there you go. Which probably divides even further. No, yes, maybe. It should, no. I feel like I'm, not to, yeah. I feel like I'm making some dumb mistake. If I divide that by 3 and that by 3, I should get a 2. What crazy thing am I doing here? I'm doing something. I'm done. Wow. Yeah, my brain. Sorry. If I divide that by 3, I get 333,333. If I divide that by 3, I get 2. Okay, that's much better. That's something wrong here. On the other hand, you could do this thing where you change the limits of integration, which I think is the better way to do it. If you have a choice, I would take you with this way. So we're still going to do the same integral. It's going to be the integral of u to the 5th du. But we're also going to do the thing where we say, well, look, I know that if x equals 0, well, u is x squared plus 1. So if x is 0, u is going to equal 0 squared plus 1, which is 1. And similarly, if x is 3, u is going to equal 3 squared plus 1, u is going to be 10. So then our limits of integration are from 1 to 10. And now we're going to integrate this. We're going to get u to the 6th over 6 between u equal to 1 and u equal to 10. And here's the really important thing to remember. You do not have to change. In fact, you cannot change back to x's. You have to leave it in terms of u because these are the u values. So just plug in 10, you get 10 to the 6th over 6. Plug in 1, you get 1 to the 6th over 6. Hey, look, that's the same answer as right there. So I think this is better. You don't have to plug back in. It just feels a little bit cleaner. So this is the way I would encourage everyone to do definite integrals where you have to use substitution. Change the limits of integration to use and don't change back. Let's look at an example of this. Or another example, I should say. Let's say we want to find, is that up there? No, piece of plastic. Oh, sure, let's do that one. Let's do the integral from, oh, where'd you go? Sorry. 1 second here. X squared over the square root of x cubed, 1 minus x. Sure, x cubed plus 1 from 0 to. Yeah, that should not be too awful. So what's our choice for u? I mean, there's only one good looking choice. I'm going to pick, you're going to pick, we're all going to pick the thing that's stuck inside the square root. And not just because it's stuck inside the square root, because its derivative, the derivative of x cubed is 3x squared. So du is 3x squared times dx, and we have an x squared times dx. So 1/3 du is equal to x squared dx. So I can rewrite my integral as the integral of 1/3 du, and then 1 over the square root of u. And I can also change my limits of integration. Not only can I should. So here, right? If x equals 0, then u is 0 cubed plus 1, which is 1. And if x equals 2, u equals 2 plus 1, which is 9. So we're doing the integral from u equals 1 to u equals 9. Sometimes people even write that these are x limits of integration and that these are u limits of integration. But now, since our limits of integration match our variable, we don't have to change back. We just be like, hey, look, this is 1/3 the integral from 1 to 9 of u to the negative 1/2 du. We're going to anti-differentiate that. We're going to get 1/3 u to the 1/2 divided by 1/2 is multiplying by 2. Sorry, it's a little tight there. From 1 to 9. So that's going to be 2/3 times 9 to the 1/2 minus 1 to the 1/2. That's going to be 2/3 times 3 minus 1, which is going to be 4/3. There you go. Yeah. Let's look at another one.
James, I was wondering if you could flip back to the back side of the whiteboard real quick.
1 second.
Okay, thank you, James.
Oh. All right, 1 second. So let's see. We have, let's do, okay, I don't want to make this time let's do integral of tangent of x from, let's make it more, no, let's do tangent of x. Let's do tangent of x from pi over 6 to pi over 3. Okay, so for tangent of x, we have to rewrite it as sine of x over cosine of x. So let me ask you guys, what should we choose for u? Should we choose u equal to sine, or should we choose u equal to cosine? Both seem like pretty decent choices, right? Derivative of sine is cosine, the derivative of cosine is essentially sine, right? It's negative sine. So, what should we choose? Well, let me show you. So let's say we chose u equal to sine, right? Often people are like, oh, let's pick sine because its derivative is positive. Well, sine's not going to work. If you pick u equal to sine of x, your du is cosine of x times dx. And I want to be very, very explicit. We don't have that. We don't have cosine of x times dx. We have 1 over cosine of x times dx. So you could totally, if you wanted to, rewrite this as the integral of sine of x times 1 over cosine of x times dx. That is not the same as that. So instead, we can't pick that. We're going to pick u equal to cosine. And so what I really want to say here is generally, if you have a choice between picking something in the numerator and the denominator, you want to pick the thing in the denominator because the thing in the denominator is the thing that's stuck. And the thing in the numerator is not. It kind of moves about freely. So if I pick u equal to cosine, my du is going to be negative sine x dx. And negative du is going to equal positive sine of x dx. So I can rewrite this integral as the integral of, let's see, sine of x times dx is going to be my negative du. And I've dealt with the sine of x times dx. I still have the 1 over cosine, which is going to be the 1 over u. All right, and now I should also change my limits of integration. So if x equals pi over 6, u is going to equal cosine of pi over 6, which is the square root of 3 over 2. And if x equals pi over 3, u is going to equal cosine of pi over 3, which is 1/2. Now, it doesn't really matter, but I will point out that 1/2 is smaller and square root of 3 over 2 is bigger. If you wanted to, you could change the order of integration. You could say, oh, this is, oh, look, I've got a negative sign out there, which even makes it more convenient. This is going to be positive integral from 1/2 to root 3 over 2 of 1 over u du. How about that? So then this is equal to the antiderivative 1 over u is the natural log of the absolute value of u from 1/2 to root 3 over 2, which is the natural log of square root of 3 over 2 minus the natural log of 1/2. And if you combine those, you can write that as the natural log of the square root of 3 over 2 over 1/2, which is just the natural log of the square root of 3, which is just 1/2 natural log of 3. You really want to make it as simple as possible. Okay, how about that? Let's see, it's 350. So let's see here. What was I gonna say? I did want to point out, because it does come up later on, this particular integral. So in general, if you're just integrating tangent, right, so back to indefinite integrals, the antiderivative of tangent of x, well, the process is still the same. You would let u equal cosine of x. Du is going to be negative sine of x dx. Negative du is sine of x dx. So this is equal to the integral of sine of x over cosine of x dx. That right there is your negative du. This becomes the negative integral of 1 over u du, which is the negative natural log of the absolute value of u, which is the negative natural log of the absolute value of cosine of x. That is your antiderivative of tangent. I will also point out that you could rewrite this as the as the natural log of the absolute value of cosine of x to the negative first power. But when you have something to the negative first, you can do its reciprocal. So this is the natural log of 1 over the absolute value of cosine of x. But this is equal to the natural log of the absolute value of secant of x. The reason I mention this is because both ways are considered correct ways of writing the answer, and both are often written. Sometimes we like to write it this way as negative natural log of the absolute value of cosine of x. Sometimes we like to write it this way as the natural log of the absolute value of secant of x. They both come up. A couple tricky integrals, and then we'll call it a day.
Wait, James, could you turn the whiteboard for a quick sec?
Good.
Yes, thank you. Thank you, James.
So Here's one that's tricky if you've never seen the trick. I feel like we might, you know what, I think we talked about this one already. I'm going to do it real quick. Tangent squared. I feel like, yeah, I think this one came up last time. The integral of tangent squared, you use the trig identity I tan and gets x, or 1 plus tangent squared x equals secant squared x. And you solve for tangent squared. Tangent squared x equals secant squared x minus 1, which is equal to the integral of secant squared x minus 1. We know the antiderivative of secant squared is tangent of x. And we know the antiderivative of 1 is just x. So really easy if you know the trick, challenging if you don't. The other one I want to mention is something like this. Something like 2 over e to the 2x plus 1. This problem is a U-substitution problem, but it's in disguise. So as is, if you let u equal the bottom, you're not going to get anywhere. If you let u equal e to the 2x plus 1, your derivative is 2e to the 2x plus nothing. And so your du is 2e to the 2x dx, but I don't have that anywhere. So here's the trick for a problem like this, where you have like something over e to a power plus a constant. You're going to multiply the top and bottom of this expression by e to the opposite sign power of this. So if I get e to the 2x, I'm going to multiply by e to the negative 2x over e to the negative 2x. So let's look what happens. On top, you get 2e to the negative 2x. On the bottom, e to the negative 2x times e to the 2x is e to the 0, because you add those powers. And e to the 0 is 1, plus e to the negative 2x times 1 is e to the negative 2x. So then we're going to let u equal the denominator. So instead of u being e to the 2x plus 1, it's actually going to be 1 plus e to the negative 2x. And the du is going to be, well, the derivative of e to the negative 2x is negative 2 times e to the negative 2x dx. And look, I have that almost exactly. I just am missing the sign. So negative du is positive 2 e to the negative 2x. So this, with the dx, right, that's my negative du. So I've got integral of negative du over u. Put the negative on the outside. That's going to be negative natural log of the absolute value of u. Plus c. And then plugging back in u, it's the negative natural log of the absolute value of 1 plus e to the negative 2x. Plus c. So again, this is an example of a tricky integral that comes up somewhat often that's not too terrible to deal with if you know how to deal with it.